Hello, this is 1.3 intersection and union problems. So we're just going to continue with the context-based problems that involve these two ideas, and so the notes get us started here. You can see here the key ideas. We have the union, and it's demonstrated on the left and the right. On the left, this is the union where the sets are not disjoint. On the right here, this is the union when the sets are disjoint. And so when you look at the shading, that's what you're interested in. So you can see that everything gets shaded. Now the intersection, same idea here. On the left you have the not disjoint, and on the right you have the disjoint. The next idea, the big idea, is intersection. And so you can compare the two symbols. Remember, that's union, this is intersection. Okay, compare the language. You got or, we got and. So the intersection, these are the elements that are members of both sets. And so when sets are not disjoint, the elements that are members of both, that's what we call the intersection. And so if you look, when two sets are disjoint, they have nothing in common, then we would say that their intersection is empty. In other words, there are no elements that are in both A and B at the same time here. Need to know this formula. Two situations given. So, if two sets, A and B, contain common elements, so this is the not disjoint case, so they do overlap, they're going to say that the number of elements in A or B, which is shown here on the left, the number of elements, that's the lowercase n, number of elements in A or B is equal to, okay, so you just add up all of A, you add up all of B, and then you're going to subtract those values that got counted twice. So that's the intersection. And the reason we subtract it is because, like we've been saying in the last couple of videos, is we don't count things twice. And so when you're doing this in practice, all of the elements in A, you count them. All of the elements in B, you count them. And then you can see that some elements will get counted twice, so you just have to subtract those out. Now when the sets are disjoint, you don't actually have to worry about counting up the union that way, because you don't have to subtract anything. In fact, you'd be subtracting the empty. And so the second one here, the second major key idea, if two sets A and B are disjoint, they contain no common elements, and so their intersection is empty. And then when you add them up for the union, when you're trying to find that union, you just add up all of A and you add up all of B, and you don't have to worry about subtracting anything because you're subtracting 0, and so you get that formula there. And here's the third key idea for counting up the union, okay? And so that's given here at the end. Elements that are in set A but not in set B are expressed A not B. So that's right here, A not B. And another way that they write that, like that's the way the textbook writes it, they would say A and not B. And so these two ideas are the same. And it's basically the A only. A and not B. Okay, and so getting that out of the way, we can now look at a third way of expressing how to count up the union. So that's right here. The number of elements in A or B can also be determined as follows. And so I'll show you this with a picture. And let's say this is A, and this is B, and let's use some easy numbers. This is 1, this is 2, this is 3. So if you wanted to count up the union, which is all of A, all of B, then you can actually just count these up piece by piece. So if you look at this one, this first term, this one says A only, so that's the 1. Then this one here's the B only, that's the 3. And then here, that's the intersection, that's the 2. And so moving ahead and moving forward, if you want to count up a union, you can just count up each individual part. So 1 plus 2 plus 3 equals 6. If we follow the ways of doing it up above with this subtraction piece up here, then I'll show you that way as well. So you add up all of A, so that's 3, 1 plus 2. You add up all of B, that's 5. And then you subtract the middle, which is this 2. And so you get 6 in either case. Alright, so let's take a look. In a homeroom of 20 students, so that's our universe, 15 take math, and 12 take social. So I'm going to label my diagrams M and S. So that's set 1, set 2, math and social. And so when it says 15 take math, the number of students that take math is 15. What they're saying is these two sections, when you add them up, you're going to get 15. It doesn't mean you put 15 right here. That's the most common mistake that we want to avoid. The entire set itself has to be 15. Okay, so 12 take social. Same idea over there. And then it says 10 take math and social. So the number of students that take math and social, that's the intersect, is 10. So I can put 10 right in the middle. And so if you follow the hint on the right there, it says always start in the middle of the Venn diagram and work your way out, if you can. So if you know the middle, then if 15 take math and 10 have already been counted, that must mean there's 5 there. And if 12 takes social and you've already got 10 accounted for, then that must mean 2 takes social there. And so when we look at these numbers, 5 took math only, 10 took math and social, and 2 took social only. And so when you go to count up the union, so the number of the union, M or S, you can just add them all up separately, 5 plus 10 plus 2. Or you can add them up set by set. So there's 15 that took math and 12 that took social. And then if you subtract the 10 in the middle because you don't want to count twice, you get the same value. And then there's the last thing that we have to cover. If there's 20 in the home room and there's 17 in the union, then the number in the union complement will be 3 because 20 take away 17 is 3. And so we have it all accounted for. One last check. 5 take math only, 10 take both, 2 take social only, and 3 take neither math nor social. And if you add all these up, you should get 20, the maximum, the number of the universe. We're going to skip 2 for now, and I know that this isn't the same in your book. There was a typo. So we're going to try this next class example here, just to really reiterate all the key points that have been brought up to this point. So let's start listing the elements that are in P. So we need 2, 9, and 8, as well as 10. Don't forget about that. All of Q, so that's 7 and 29, as well as 10. P and Q, that's the intersection. P or Q, so this is everything in P, everything in Q. Don't count the 10 twice. Not P, So we have everything that's the complement of P. So everything that's not in P but in the universe. So of course 7 and 29 are not in P, as well as 11 and 16 on the outside. Not Q is done similar way. So elements that are not in Q, we have 2, 9, 8, 11, and 16. Okay, these next two symbols represent P and Q naught. So to do that one, I'm just going to find P and Q, and then this little symbol there means I want the opposite of that, so the complement of that. So it's going to be everything else. So I got 2, 9, 8, 7, 29, 11, and 16. So that's the complement of the intersection. Okay, and then now I want the complement of the union. So let me just find the union. And now to do the complement of that, I would do everything else. So that's just the outside, 11 and 16. So this Venn diagram here, I'm just going to tell you that it's similar to the one we did on the last video. And so they're telling you all of the elements of two sets, and they're telling you the neither nor. And so when you look at the sum of all that, and you're deciding whether you should draw it overlapping or not, like, I don't know if these two sets are disjoint or not. When you add everything up, 20 plus 14 plus 16, you will get 50. So that's the number of the universe. Oh, pardon me. The number of the universe is established at the top there. This person surveyed 45 students. But when we went to add everything up, we got more than 45. The universe is 45. That's how many people were actually surveyed. And then when I look at the data here, I can see that I've counted up to 50. So that must mean that these sets are not disjoint. So I can draw them overlapping. This one's cricket, this one's polo. 16 is established on the outside. That's the neither nor. And then remember, we don't put 20 and 14 like this. That's incorrect. What we know is that this entire set will add up to 20, and this entire set will add up to 14. And we need to find out the middle. To find out the middle, you just subtract the total that you added up by the universe, and you get 5 here. So that's how many people were counted twice. And so now I can see that this is 15 because it has to add up to 20, and this is 9 because it has to add up to 14. So how many students like cricket and polo? So that's 5. And how many students like only cricket or only polo? So let me highlight these with blue. Only cricket is 15. Only polo is 9. And then when we say or, what we really mean is add it up. And so that's 24 total. So many of these questions are similar and you'll get good practice. This one's a little bit different, so I'll show you. 80 people surveyed about their ice cream preference, so that's your universe. The results are shown below. Determine the number of people that liked only chocolate. And so when you're reading these questions, if you come across the word only, you got to be very careful that you pick it up. So it says 9 people did not like either. 11 liked both vanilla and chocolate. So these tell us that we have an intersection. So the intersection is not empty. So they do overlap. Some people like both vanilla and chocolate. In fact, 11 do. So there's our universe outside of these two sets, and we know that 9 do not like either. That was from there. And the only one left here is the 20, like only vanilla. So now it's safe to put 20 there because it says only vanilla. And so if the universe is 80 and I have those other 3 sections accounted for, and there's only 4 sections total, I just need to subtract 20, 11, and 9, and I'll get the number of people that liked chocolate only. And it says here that that's 40. So that would go there. The next question, and the last question I'll do for this video, is an example where the sets do not overlap. And that's one thing that you get into a habit of doing these questions, is you just automatically think that they overlap. But each question is different onto its own, and you don't know if the sets overlap or not until you read it. So Paul asked 20 students whether they have a dog or a cat, and here's his results. 4 students do not have a dog or a cat, so that's going to be on the outside. And you can sort of think of it as like a running total. So 4 has been accounted for. We have 16 people left to fill. And so it says here that 8 students have a dog and 8 students have a cat. And so when you go to total those up, you're going, okay, 8 plus 8, and that's 16. And so when you look at these two values, you're thinking, oh, they're the exact same. Nobody got counted twice. There isn't an overage. Like usually when the sets are not disjoint and you add everything up, you get an overage. Like here, 50 here was greater than 45. So by how much? Well, that goes in the middle. And so we don't have that happening in this last question. When you go to add everything up, 4 plus 8 plus 8, you get 20. Or if I place the 4 there, now I only have 16 left, and it's like 8 and 8 is 16, then there's no overlap. Nothing got counted twice. And so these people have, I guess, set up a situation where there's disjoint sets. So there's 8 that like or have a dog, and 8 that have a cat, and 4 that have neither. And so then the question is, how many students have both a dog and a cat? So these are the students that have both, and we see that the intersection is empty. There's nothing there. So the answer here is 0. There's no student that has both a dog and a cat.